There's a button. There's a button, right? Okay, yeah, then it's got it.
Oh, because I had a key. Yeah, that's a key. It's stuck. It shows the actual.
So it sounds like people can hear me. At least that's what the chat room is saying. And is there any feedback today, or is it loud enough? No response is a positive response. So, I share my screen. And then bring up today's presentation. And as you know, there was one handout for today. And that handout, hopefully you have, as you're going through at home. And also, as always, for the last 3 lectures, this is going to be on the 3rd exam. So, without further ado, we've been talking about, up to today, flat plates. And for flat plates, what we recognize is we have this free stream, and that free stream is coming in at some velocity, capital U. It can be any letter. The most conventional ones you see is capital U or capital V. And again, this is just by convention. That's about it. The most important thing is once that free stream velocity hits the leading edge, the boundary layer starts because of the no-slip condition. And all the boundary layer is a region where the velocity is changing from that of the boundary to the free stream. Again, all precipitated by that no-slip condition. If we didn't have that, we wouldn't have this. And again, what the boundary layer is a communication zone where through the fluid, there is a signal being communicated. What's that signal? Somewhere in the fluid, we have a different velocity than the free stream. It is a relative velocity issue, obviously. If this plate was moving at capital U in the same direction as you wouldn't have the boundary layer because there would be no difference in velocity. So that's all the background. And again, we focused on flat plates. And again, what we saw was the boundary layer had 3 distinct areas or zones. Initially, for the smooth flat plate, you have nice structured movement of particles. They're moving in what are called laminae. After a while, those laminae become unstable in the upper part of the boundary layer. And so up here you have mass movements of the fluid in 3 dimensions or vortices. That's known as turbulence, and this is a turbulent portion of the boundary layer. Yet down below, you still have this laminar or laminar sublayer. When we have both of these components, turbulent over laminar, we call that a transition boundary layer. And then lastly, at very high Reynolds numbers, the sublayer, the laminar sublayer disappears, and we have entirely turbulent boundary layer. And again, for a flat plate, we know where these zones more or less occur. That Reynolds number changes depending on the scenario you're looking at. But the Reynolds number is always used to distinguish between laminar and turbulent. Okay? It's just that how we calculate it and the actual values we use will change depending on the flow scenario. And you'll see this in future lectures. So, also as a refresher, helpful for this afternoon, let's think of or look at a constriction work and an enlargement of pipe. So here is the common Venturi you see. We have flow from left to right, and we're drawing streamlines from left to right. Flow from left to right. And again, what's happening is we have a large cross-section A1, it's followed by a smaller cross-section A2. And we know from continuity, if the discharge is constant, that V1, the velocity of A1, is going to be much less than V2. That's from continuity. V is equal to VA. At the same time, if we have an energy grade line here that's constant, no energy losses, a pressure gauge or a piezometer is giving us, I should do this in a different way. The piezometers are giving us the hydraulic rate. And again, the difference between the energy grade line and the hydraulic grade line is V squared over 2G. Before and after the constriction, we have V1, and in the constriction, we have V2. Great. Now, that's all review. What I want you to focus on is the streamlines, are the streamlines themselves, and the spacing between the streamlines. When we're in a large cross section, the streamlines over here are nice and parallel, but they're farther apart than when the streamlines are close together. You see that, right? And wherever we can draw a path line, we can write an energy balance. Conclusion, streamlines far apart, pressure high. Streamlines close together, pressure low. Got that? Again, this is all, I might actually have this. Yeah. Focus on the streamlines and how they relate to changes in velocity and pressure. So close spacing. What we have is high velocity and low pressure. And large spacing. We have low pressure, low velocity, and high pressure. Okay. And all that's happening here is you're converting one form of energy to the other. But again, I want you to focus on the streamlines because that has everything to do with what we're going to talk about now in three-dimensional. So let's consider flow moving by a sphere. And here you can see some streamlines. And obviously, as the streamlines move around the sphere, what you start to see is their spacing is changing. And all I want you to remember is spacing far apart, low velocity, high pressure. Spacing close together, high velocity, low pressure. Why? Because if we look at the energy here on any one streamline, we can equate it to the energy somewhere else. So all we're going to do is look at the total energy along the streamline. And just like in the constriction and expansion in the Venturi, those streamlines were telling us something about what was happening with velocity and pressure. So again, for this definition, and you're going to see this on like the next 20 slides, basically this system. We're going to have a free stream velocity capital U, just like we did for the flat plate. Only now, instead of coming onto a flat plate, it's trying to go around a sphere. There's a leading edge to the sphere and trailing edge to the sphere. The sphere is sitting still, the fluid is moving by it. As soon as the fluid comes in contact with the sphere, the no-slip condition is operative and a boundary layer starts. The fluid has fluid properties, density, viscosity, kinematic viscosity. And then lastly, the sphere diameter is going to be capital D. I think that's all pretty easy to understand. For this system, we will define the Reynolds number a little bit differently than what we did on the flat plate. A Reynolds number is always a velocity times the length over kinematic viscosity of the fluid, always. In this case, the velocity is the free stream velocity. The length here is different than the length of the flat plate. For the flat plate, the length parameter was the distance along the flat plate x. In this case, we use the diameter is the sphere as our length parameter. That's how we will define the Reynolds number. When you had a laboratory exercise where you were calculating Reynolds number for the flow of pipe, you basically used this equation. The length parameter was the inside diameter of the pipe. Again, Reynolds number is always a ratio of forces. And those ratios are inertial forces to viscous forces. And it's always the velocity under length divided by kinetic velocity. So we're going to start at a very slow velocity where the Reynolds number is 0.01. And so here is our sphere, and here are some streamlines around it. And again, it's not really easy to see, but you know, in the vicinity of the sphere, you start to see changes in the spacing. However, they're not that dramatic. So at this Reynolds number, we have a laminar boundary layer over the entire sphere. And because there's a laminar boundary layer, that means there's a velocity profile. Because there's a velocity profile, there must be shear stress, particularly shear stress right up against the surface of the sphere. And just like on the plate, we call that tau zero, the shear stress where y is equal to 0, right on the surface of the object. If this scenario was sitting here, the sphere was sitting here, and the flow was moving by it, it would push that sphere in the direction of the flow. So we would need to have some type of a restoring force to hold that sphere in place against the forces of the fluid. What are those forces? It's the shear stress all over the area, integrated over that area. It's a drag force. So the equal and opposite force to that restoring force is the drag force. So again, force equal and opposite to this restoring force, the drag force. And that's, those two forces are in equilibrium. That's why the particle stays where it is. If you did not have the restoring force, at this instant, the drag force would then start pushing the particle in the direction of the flow. And as that particle starts moving, again, it's relative motion. You would have a velocity of the particle, you would have a velocity of the fluid. And the difference between those two is the relative velocity. And ultimately, if the particle moves at you, there's no more drag force. The system's in equilibrium. This is the same concept we will use in setting, designing some of the first components to wastewater water treatment. So again, all of the drag on this sphere at this Reynolds number is due to frictional resistance. But wait, there's more. There is similarity or symmetry in these flow lines from upstream to downstream. That's actually pretty important. There's symmetry. So even though they may be spaced a little bit farther apart, since it's symmetrical, there's really no difference in pressure from the front to the back. So now we're going to increase the Reynolds number about 2 orders of magnitude. It was 0.01 before, and that's 3 orders of magnitude. We're going to go up to 20. And this is what's happening. We now see that these streamlines are moving around the sphere, but also a really interesting thing is happening at this location and right behind the sphere. So we need to discuss that. At the leading edge, we have a laminar boundary layer. So we start off with laminar, and then afterwards, it may convert to a transitional, to the transitional boundary layer. So the blue is the laminar, and this is occurring all over the front surface of the edge of the sphere. And all the rest has a transitional boundary layer over it, from the end of the laminar all the way to the end of the sphere. At a certain location, the boundary layer at this location and remember, since this is a sphere, that separation point is a circle around the trailing edge of the sphere. there's a location where the boundary layer strips off of the sphere. We call that the point of separation. Why does that happen? Well, remember, fundamentally, the boundary layer is a zone of communication. It's where the fluid is transmitting a signal that somewhere there is this location of a very different velocity, the boundary in this case, the sphere. And that signal is communicated in a laminar boundary layer through Brownian motion, because in laminar flow, you have fluid moving in nice straight structured lines. Once you have turbulence in the turbulent boundary layer, in the transitional boundary layer, you have the turbulent zone above the laminar somewhere. That signal is processed by mass movements of fluid through the vortices. And that's actually much more efficient than trying to transmit that signal through Brownian motion. But again, fundamentally, when you have the transitional and laminar boundary layers, at the location between the object and the fluid, there's a laminar. It's either the entire laminar boundary layer or the laminar sublayer transition. And that is not a very efficient way of transmitting the signal. And what's happening? So here, the spacing between the path lines can be considered our base case. Here, right on top of the object, at this location, we have closer spacing. And remember, what closer spacing means is that the velocity went up and the pressure went down. That's why I asked you to focus on the previous one. And then when you get past the point of separation, you still have that closer spacing. So the point of separation occurs where the boundary layer is unable to keep telling the rest of the fluid there's this solid boundary down there. And when it's unable to do that anymore, it's a molecular momentum exchange issue. The only thing the boundary layer can do is strip off of the sphere and move out into the fluid as an intense zone of shear. And what it leaves behind is what we call a wake. And there is fluid movement in that wake, but it's not any movement in the general direction of flow. It's not stagnant, but it's filled with fluid, but it's not contributing fluid flow with the rest of the system. And so what you have, because of this wake, immediately close to the wake, the streamlines are still closer together. The pressure is lower. And now what happens is you have a pressure upstream, which is greater than the pressure downstream. Now you have a pressure difference from front to back. And if you take a slice through this and look at the sphere as a circle, I think a long time ago on Faraway Place, we talked about forces on plane submerged objects. In this case, you have a circle with one pressure on one side and one pressure on the other. The pressure upstream is greater than the pressure downstream. So after the boundary layer separates, downstream you have a wake. And the fluid movement in that wake is nice and structured. It's laminar, so we call it a laminar wake. Continuing with this same figure. The pressure in the wake, pressure here, is typically equal to the pressure immediately outside of the wake. Again, that's why there's a pressure difference from upstream to downstream. The pressure upstream is greater than the pressure downstream because of that. And the pressure that's dictating the pressure in the wake is the pressure immediately outside of the wake, where the streamlines are still close together. And therefore the pressure is lower. I think I've explained the analogy. And again, because of the wake, pressure upstream is greater than pressure downstream. I think we said on the last slide. So overall, in the earlier Reynolds number, There was no wake. All of the resistance, all of the drag force was due to friction. In this case, we have a larger drag force. However, the drag now has two components. One is due to friction. That's where the boundary layer is running in the surface. But the other is what we call form drag. It's due to the difference in pressure from front to back. So drag on any object, even a flat plate, has these two components. It's just on the flat plates. We never had a wake. They were so thin, we would never get a wake. And so on the flat plates, all drag is frictional because there is no wake. Whenever you don't have a wake, you do not have form drag. And when we look at this, the frictional drag is actually much greater than the form drag. Much greater. So put two of those in. All right. Now we're going to bump up the Reynolds number a little bit. And we're going to go up to a Reynolds number of 100. And the first thing you see is this dramatic occurrence happening downstream. We're going to talk about that. But what happens is the wake is in here. And the separation points have moved forward. By moving forward on the object, it increases the size of the wake, both in thickness and in length. As before, the boundary layer at the very leading edge of the sphere is laminar. And as it moves along the sphere, it becomes transitional. But before it can actually go into turbulence, it strips off again at the point of separation. The fluid movement in the wake is still in. It's just what is The weird thing about this is what's happening is on alternating sides at the point of separation, a vortex grows and then strips off and moves off into the fluid. It moves off into the fluid as this little swirl. As the vortex is growing on one side, it's increasing the size of that wake, especially perpendicular to the flow. And since it is not symmetric now, it's asymmetrically causing a force in the direction normal to the fluid flow, capital U. I would argue you've seen this before and you've never thought about it. So this vortex shed is known as von Karman's vortex sheet, after the scientist who first described it and tried to explain it back in the late 1800s. Again, the asymmetric wake shape is creating force in addition to the drag force. The drag force is a force collinear with U. This other force is perpendicular. And when you look at something that's doing this, this is what the wake is looking like. So again, all of this is in the wake, and you have these vortices occurring, alternating, which at any particular time makes the wake shape irregular. How many times have you seen a stick in a stream that's flowing just bobbing? That's why it's bobbing, because of this normal force in von Karman's vortex shedding system. How many of you have ever taken a blade of grass and put it between your thumbs and blown on it? What the U, capital U, is what you're blowing, and what you're doing is creating this vortex sheet and making the grass vibrate. They also call them singing telephone wires, and high enough wind speeds, the telephone wires also start to vibrate. Same reason. So again, you've seen this before. We're just trying to describe it and ultimately use equations to help us with what's important to what we're doing. So a lot of this is all descriptive. So again, we're still at the Reynolds number of 100. And for the drag compounds, we still have friction and form drag. But remember, what's happening is because of the layer of separation is moving forward on the sphere, the zone at which you get friction is shortening. So friction drag is becoming smaller, but because the weight is increasing, the form drag is increasing. Overall, total drag is increasing compared to lower Reynolds numbers. So at this Reynolds number, friction drag is on the order of form drag. And, again, I would say the drag at a Reynolds number of 5,000 is greater than the drag at the Reynolds number that we just looked at. Okay, so drag just keeps increasing as we keep increasing. That's an important concept for you to recognize. So now we're going to go from the previous 100 up to 5,000. And at 5,000, an interesting thing happens. One, the points of separation move further forward. So this was 100. And so we draw our sphere here, and we see that our point of separation is, say, right here. Now the point of separation is moving a little bit further forward. So the points of separation have moved forward towards the leading edge. The drag zone is increasing. So by having the separation points move forward, you increase the size of the weight. Increasing the size of the weight further exacerbates the pressure difference from front to back and over a much larger area. So you're dramatically increasing drag force, form drag force. The boundary layer starts at the leading edge as laminar and moves to transition. Now what you have in the wake is a zone where you have laminar and the rest turbulent. So right behind the sphere, you have nice laminar or regular structured movement of particles, and that's in a laminar subwave zone. And then outside of that, you have turbulence, and you still have a vortices off of this, being generated on the sphere, and off from the So the vortex shedding continues, and in fact, people have developed meters. The frequency of shedding is proportional to the velocity. So you can actually estimate the stream velocity, the free stream velocity, just from measuring that frequency. So for example, you could have on a ship or an airplane, just a wire that's vibrating. And by measuring the frequency of that vibrating wire, you can get the velocity of that object. Or you can use a pitot tube, like we discussed before, and use pressure to recognize that from converting a ball V squared over 2G P over gamma, you can measure velocity. At this Reynolds number, you still have both components of drag, friction and form. Because the points of separation are moving close to the front, friction drag is incredibly small. And at this point, at this Reynolds number, form drag, difference in pressure from front to back, is larger than the friction. So we're almost done. Drag keeps increasing over all the previous ones. So total drag force just keeps increasing as we increase the Reynolds number. How are we increasing the Reynolds number? Reynolds number is U times the diameter over there. So if we keep the same particle, we're not changing the diameter. If we keep the same fluid, we're not changing the kinematic viscosity. So how we can increase the Reynolds number is just by increasing the velocity. Remember, we started at 0.01. So you're tremendously increasing velocity. In practical sense, we can do a lot of things to create different Reynolds numbers, and we can change all three of these. So I don't know if you know it, but behind Gregg Hall is a wind tunnel building. That building has a room with a cross-section almost this size, and it is just to study boundary layers. That's what that building is for. And the walls are not parallel because they want a constant flow, And so the walls have to grow as the boundary layer. Okay, we're going to change the toilet building. Very interesting. There's probably, that's probably the only building of its size in the world. There's another facility in Australia, similar size to this one. So, Reynolds number of 100,000. Now what's happening at a Reynolds number of 100,000 is the points of separation are moving further forward. And that, of course, increases the size of the wake, which will further increase the pressure difference from front to back. The boundary layer is laminar at the leading edge and transitional afterwards. So we still have not achieved a completely turbulent boundary layer. That's an important concept. The fluid movement in the wake now is all turbulent. So at this Reynolds number, we have no more laminar subwake. At the previous Reynolds number, which was 5,000, we have laminar subwake. So that's just maybe more importantly, the vortex shedding intensifies. And now friction drag is much, much less than form drag. That difference in pressure from front to back is. Again, the total drag force just keeps increasing. So we're now going to go to 10 to the 7, 10 million. Somewhere between the last one, 10 to the 5th, 10 to the 7th. An interesting thing happens. You will see the boundary layer has moved backwards. It's moved more towards the downstream side of the sphere. That decreases the size of the wake, which in turn decreases form drag. The wake itself is all turbulent. All the fluid in the wake is not contributing to the overall flow field. It's just randomly moving erratically in the wake zone and in Euler's space. Any of you who have a van or a high-profile vehicle, you know on the downstream end, that's where all the dust collects, all the dirt collects. When dirt gets into the wake, that's where the wake is. It's just going to hang around there, and it keeps colliding up against your vehicle and ultimately attaches. The boundary layer now goes from laminar at the leading edge to transitional to turbulent. You have finally achieved a turbulent boundary layer on this object. That is what actually helps the boundary layer reattach. Remember, when you have the laminar boundary layer or the laminar sublayer, how the signal is processed through the fluid is by Brownian motion, because the fluid is moving in laminar. That's not a very efficient communication tool with fluids. Compare that to turbulent motion. In turbulence, you've got mass movements of fluid that can easily communicate there's a solid boundary. And so the turbulent boundary layer is much better at communicating this signal that there's a boundary down there. And that's why the boundary layer can reattach. It's capable of staying on the object for a much longer distance to make that communication. At this Reynolds number, there may be vortices, but it's really unstable. So you're well past the range where it's something that's predictable. Because of the boundary layer reattachment, again, there's a dramatic decrease in the size of the wake, and therefore a dramatic decrease in the drag force. So, a long time ago, this week, we talked about drag force on flat plates, and this was the drag force equation. The drag force in this case was all shear. Friction. Why? Because the boundary layer was over the entire flat plate, and there was no wake. Without a wake, you don't get a change in pressure from the front to the back. So all the drag force is shear, and C sub F is a drag coefficient. But that lower case or the subscript on C is indicating it's a drag coefficient only due to shear friction. A is the area over which the friction is occurring. Rho is the density of the fluid. U is the free stream velocity, the relative velocity between the free stream and the fluid. For 3D objects, whether it's a sphere, a bicyclist, a parachutist, or any three-dimensional object, your drag equation looks very similar. The only difference is now we have capital C sub D, which is the drag coefficient, but it's compared to C sub F, where C sub F only accounts for friction. C sub D accounts for everything, friction and form drag. Again, C sub D is known as the drag coefficient, and the drag coefficient is basically a function of shape and sometimes Reynolds number. And again, on your handout for today, and bring that handout Monday, have the handout ready for Monday, because we're going to be doing examples Monday. I'm trying not to overwhelm you with equations today because you're already stressed out. So, A is the object normal to the velocity vector. So if it's a sphere, we don't have to worry about what the size of the wake is. Everything is related to the size of the wake, et cetera, and the drag coefficient. We just mean physically the size of the object. Flagpole, submarine, train, any of these are three-dimensional. So in flat plates, this was on your handout for flat plates. It's also stolen right from your book. And I want you to focus on the laminar zone, which of course is where the Reynolds number is less than 500,000 for the flat plate. And what you see is in that zone, if we just pick a location where the Reynolds number is constant, we see that the drag coefficient or friction, C sub F, is much less. Here it's half that of the drag coefficient when we roughen the surface, trip the boundary as it's called. So the solid line is for smooth, and the upper line is for a roughened surface. So if you're only worried about frictional resistance, when you roughen that surface, you're going to pay a penalty in drag. And again, this laminar line continues. It's just that at much higher Reynolds number, you can't preserve laminar. So now let's compare that to a sphere. And this is the first figure in your handout today. There's also a figure like this in your book. And what you have is the drag coefficient. Remember, the drag is equal to 1/2 C sub D rho A. And so what's happening is you see this drag coefficient starting at about 200, and it goes down about 5 orders of magnitude. So you have a laminar zone, and we'll talk about where that is. You have a transitional zone, and what are we talking about when we say laminar, transitional, and turbulent? We're talking about the boundary layer. So if you have an entire laminar boundary layer over the sphere, you're going to be in one zone. You have a transitional boundary layer, which may include laminar and the leading edge, in the middle zone. But notice what happens between 10 to the 5th and 10 to the 6th. One of these is for a cylinder and one's for a sphere. So if we look at the sphere, we go from a drag coefficient of about 0.4 down to a drag coefficient of about 0.8. That's a dramatic reduction. It's an order of magnitude in the drag coefficient. And if the drag coefficient goes down, where all these others are almost very, very similar, and there's a very small increase in the velocity, gets you almost an order of magnitude increase in the drag coefficient. That's actually an important location. That's where you get boundary layer retention. I would contest that you have experienced this everywhere. So, anybody know what this is? The golf ball, right? In fact, I stole this from Dr. Collins before he ever used it. So, golf balls have dimples. Why do they have dimples? Well, the dimples take what normally would be a smooth sphere and roughen the surface and create a turbulent boundary layer of the whole sphere. That turbulent boundary layer makes the wake zone smaller and has more reattachment, and therefore dramatically reduces the drag coefficient, which translates to if you hit a smooth surface golf ball, it won't go as far as this one with the same hit. That hit is basically the restoring force, or the opposite of the drag force. And, every manufacturer is going to have their own dimples, their shapes, their depths, etc. But it dramatically affects the performance of this little thing. And that's $1 billion industry. Right? So it's no surprise why there's so many differences here. Everybody wants a better advantage. Airplane wings. How many of you have ever really looked closely at an airplane wing? You have the leading edge here. You have the airline here, here. And so on the leading edge, not uncommonly, you will see a roughened surface. That roughened surface again trips the boundary layer to minimize the drag force on the wings. However, there are also designs to maintain a laminar boundary layer almost over the entire leading surface. As long as you do not have separation, you're minimizing the drag force because it's a form drag. There are ways of keeping the boundary layer on the surface by having vents or other structural measures to even preserve the boundary layer. So you can either trip the boundary layer or you can try to keep it on the surface. The aileron is what they use for takeoff and landing. Those are flaps that go up and down. And the spoiler they actually raise up and down. That's typically when you're landing. Those are your air brakes. That increases form drag by increasing the size of the cross section. And then you have these guys at the end. Anybody know what they're called? Winglets. Von Karman's vortex sheet. Those are creating additional form drag. If you can minimize that or control it, you minimize drag. That's what those winglets are for. So you've seen all of this stuff, and it has everything to do with what we've been talking about for the last week, the boundary layer. And that's why the boundary layer is so important for almost everything we do. If we're talking about fluids or moving something through. And lastly, and most importantly, Frisbee. So Frisbee Whammo has the protection on the name Frisbee. You can't call just anything Frisbee. However, the patent they really have are on these guys, what are called the flight rings. And so if you look at these 3 different Frisbees, again, I can't pass things around this much, but if you look at them, the only one with the flight rings, the yellow one, is the Whammo product. That's because these are some of them will just have a smooth surface, a Brand X, and then there's Humphrey Flyers, and others will have some other type of roughness element. Why? They're trying to trip the boundary layer. Why? When you trip the boundary layer and you have a turbulent boundary layer, you have less weight, less drag, so the Frisbee not only flies farther, but it's more stable. So this kind of is identifying where we're going and the fact that we can engineer these systems. You can engineer them for one type of performance, or you can engineer them for another type of performance. And the other comment I made, the last comment today, I had mentioned shark skin. It's very rough for the exact same reason. They evolved to have a competitive advantage over things that don't have a roughness. So good luck this afternoon. I'm letting you out early so you've got 10 extra minutes to say your prayers or do whatever little things you do between the day. Good luck this afternoon.